Purpose of today's lesson is to talk about how the atomic theory has changed over time. The model that we have for our current atom is not the same model that we have had, all throughout history. Obviously, it's changed over time, and that's kind of the big thing that we want to take away from this. Normally, in class, we're going through this, and you have to draw pictures. But for today, you can kind of sit back and relax, just pay attention, take that short quiz at the end, and you'll be all set. So all this starts a long, long time ago, way before the current calendar that we have. Way back in 430 BC is the first time that we can find records of this and everything. And it all starts with the Greeks. The Greeks were a people group that were just completely devoted to science. They loved learning about things, inventing new things and everything like that. And while there was no one scientist that did this, Democritus was one of them. Where's my picture of Democritus? No. Oh, right here. This is believe it or not, the best picture I could find of the guy. He kind of looks like someone stepped on his toe or something like that. But anyway, Democritus, along with several other Greek philosophers of the time, they were the first ones to at least record the idea of stuff that we see as being made up of smaller parts, like my good friend, the brontosaurus right here, this dinosaur right here. If you could look at the plastic toy that it is, if we could see it's made of atoms, obviously to us. But for them, the Greeks, way back, before our modern calendar even came around, well, for them that was a totally new idea. They were, some people thought they were completely crazy to say, well, this plastic dinosaur right here, or that rock, or whatever it is that they were talking about, it's really made of tiny little things, small things. They're so small that none of us could even see them and everything, right? And they went on to say that each one of those little pieces, those little, what they called atmos, and today we call atoms, they were indestructible. It was like a tiny little sphere that was indestructible and everything. So the diagram that I would normally have you make is just something that is, like a stippling drawing. If you've ever done a stippling drawing, it's just a drawing, but it's made of individual little tiny dots, if you're poking at things and everything, right? So kind of like this picture of a crab right here, right? The crab is just dots, right? I mean, when you look at it from far away, it's obviously a crab, but as you zoom in a little bit closer, you can see it's made up of just tiny dots. And if you zoom in even bigger, the dots get bigger. And the closer you get, the more you can see. It's just tiny little dots that are making up that picture for it. Now, for a long, long time, that was the most modern theory of the atom, right? You can see, look, we're talking more than 1,000 years later, right? About roughly 2,000 years before anyone comes along and at least publishes or writes about atoms in a way that puts forth some kind of new information about them and everything. So what happened is, the English scientist, this guy right here, John Dalton, right? He was the first one to come up since the Greeks with some kind of, with some kind of new theory about atoms, new information about them. And it's only now, around the 1800s, where we finally had enough technology that we couldn't still see atoms individually, but at least we could do some experiments on them. And what John Dalton does is he finds out that, well, not all atoms are the same. There are different kinds of atoms, right? Until then, well, it was theorized that maybe just there are these tiny little atoms and they make up everything. And, that's kind of the end of it. But he was finding out, no, there's some differences about them. Some of them have one characteristic, others have a different characteristic. He described them, though, still like the Greeks, as smooth, round spheres. In fact, he often described them kind of like a billiard ball, which is a pool ball for us today and everything. So for the picture, it was just, a big round sphere. It's basically all that they had. Now, it doesn't take too long, roughly 100 years later. That's a much shorter gap in time, right? There's this guy, J.J. Thompson. Oops, I'm going the wrong way. J.J. Thompson, right? He's doing some experiments about this and everything, and he makes another big discovery, right? He's able to prove that inside of those atoms, well, there's a negative part to it, right? It's not all just the same material that has some different compounds and everything. There are actual negative parts to it. Now, JJ here, he's a college professor, and he's teaching about this. He's teaching about these atoms and everything, and he likes to do what we call the plum pudding model, right? This was the model that he came up with, right? Now, he proved there's an atom, kind of still, they still kept, the round shape of it and everything like that at this point. And he knew that there are parts of it that were negatively charged, right? So he described it like plum pudding, right? Most of the atom is just kind of there and everything like that. But there are certain places of it where there seems to be negative charges. And he knew it wasn't everywhere. It was just certain places inside of it. So for the atom picture here, there's an atom. Parts of it have a positive charge. Parts of it have a negative charge. But what JJ can't do is he can't say where the negative parts are. He just knows that they are parts of that and everything. Now, hold on here. Our next one is this guy right here, right? Rutherford. Rutherford is an American, right? And Rutherford comes along, and he was actually in JJ's class. So he's literally in science class, kind of like you're in science class and everything. And his teacher's teaching him, but his teacher says, oh, we found that there's a negative part, but I don't know where. And this particular problem, this really did not sit well with Ernest Rutherford, right? Eventually, what he does is he's got to go and create his own series of experiments, right? And he wants to prove where the electrons actually, what we call now the electrons are, right? And so what he's able to do is he's able to find out that the electrons are towards the outside of the atoms, right? So this is where we start finally getting into at least somewhat the modern model of the atom right here, because now we've got, okay, there's a center, what we'll later call the nucleus of the atom, where the positive energy is, and the negative parts of the atom, the electrons, they're focused more towards the outside of it and everything. Now, the next one that comes along is the most exciting name in our list of names today.
I got a bad feeling about
Niels Bohr. Yes, the Bohr family. Could you imagine having them over for dinner? The Bohrs are coming over for dinner, honey. That doesn't sound very exciting. But aside from his crazy name, Niels Bohr, he went on. He did even more experiments from the scientists before him. And he was able to actually do more experiments specifically with the electrons, right? Now, what he found is not all electrons are the same, right? Some electrons are a little bit slower, some electrons are a little bit faster. And so in his model of the atom, he kept it still the same like before. Hold on here, like this little guy, right? You know, nucleus at the center, electrons spinning around it and everything. But what he said is the electrons, he noticed some are slower, right? And the slower ones, he keeps closer to the nucleus. So he literally described it kind of like a map of the solar system. He said, imagine, you know, the nucleus, positive energy is the center of the solar system, kind of like our sun. The only difference being our sun's really big and the nucleus is actually really tiny. But then he said, like, some electrons are kind of like stuck really close to the sun. They're the slower ones. And then as you move further and further and further out, the electrons have more and more speed. So you get to, you know, out where, you know, some of the outer planets are. These are like electrons moving even faster than the slow ones. Don't get me wrong, the slow ones are still fast, almost the speed of light, but they get even faster the further out you go. So in the picture, you got like a little nucleus at the center, and then circling around it would be those electrons. The faster they go, the further out they go from, from the nucleus of that. Okay, it's not till the 1920s. This isn't that long ago where we make our next big breakthrough, right? The next big breakthrough is unlike what Niels Bohr said, right? Niels Bohr said some of the electrons are faster, some are slower, but he was convinced they kind of stay in these nice, neat little paths, right? You know, kind of like some of the models you see of atoms where they have little lines circling around, you know, the atom and everything like that. But we learned that electrons, they don't seem to really like to do that. In fact, electrons don't like to obey any of the rules that we set for them. They constantly are breaking normal, you know, what we would call normal physics rules. The electrons are spinning around, but they're going at literally like almost the speed of light, like literally almost the speed of light. They're going actually so fast that a better way to describe it is instead of like an electron spinning around and around the nucleus, kind of like this, they actually almost blink in and out of existence. Like first it's here, then it's over there, then it's over here, then it's over there, then it's over here, then it's over there. It's just that fast, right? So what we do is we actually call the modern model of the atom the cloud model. It's almost like a cloud. So the nucleus is still at the center. The electrons are here blinking in and out of existence. Now, we do know that Bohr was right. Slower electrons do kind of hang out just a little bit closer to the nucleus, and the faster ones are towards the outside, and they are still moving. They're not just like sitting there blinking like twinkling stars. They are still moving. It's just when we try to look at them, that's almost what it appears like. They're just almost like it's here, and then it literally just pops out of existence, and then it pops up over there. Right? So these electrons are just that unbelievably fast as they're moving around and everything. Then we're coming down towards the end here with James Chadwick, who kind of looks like a vampire. I don't know. He just reminds me of that and everything. Now, in 1933, he makes the last really big discovery about the atom as far as the major parts of it. And he discovers that in the nucleus, there's another part of the nucleus, right? You've got obviously the positive protons, but you also have these neutral neutrons. Right? And the neutrons, because there's no charge, they're not positive like the protons, they're not negative like the electrons. That's what made them super hard to actually discover and everything like that, because it's hard to do tests on those for them. Now, these neutrons, they do play a part in the atom, right? I mean, they do add some mass to the nucleus and everything, but they're not nearly as important as the protons, right? The protons you could think of as the literal heart of an atom, right? You know, without the protons, you can't have an atom. But the neutrons, we'll kind of learn a little bit later in this chapter. You can get rid of the neutrons and still have the atom, right? And so that's the major portion of that's the major parts of the atom that we have. Now, we do know more, though, right? If you want to go inside of, okay, what are the protons? Since the protons are kind of like the heart of the atom, the most important part of the entire atom, what are those made out of? So if you look inside of those, we've done enough tests, right, where we can see that inside each one of those protons, well, we know there are quarks. There are 3 quarks inside of each proton. And then there are these gluons, which, I don't know, they kind of have like these little spring-like shapes and everything is the best way to describe them, that are kind of holding them together. Right, so that's kind of what's like holding each of those together. And then, of course, as technology goes, people ask, well, what's inside of these quark-like things and everything? And so for those, now you get into a whole craziness of all kinds of weird what's called subatomic particles, right? They're smaller than an entire atom, right? And so there's a whole bunch of smaller pieces of quarks and everything like that. And then as we've got, even more, powerful instruments like the Large Hadron Collider, right? Well, now people are asking, okay, what are inside these little parts of quarks and everything like that? And then, I mean, after that, it starts getting really crazy as far as the science that goes into that. But we do know there's a whole world of other little tiny particles inside of there. And sure, by the time you guys have kids, then we'll probably have even more powerful colliders and we'll know what's inside of those things and everything. So it keeps advancing as we get better and better technology. We're able to look inside of atoms and see more and more detail. So the big takeaway for today, right? The model of the atom has not always been the same, right? It started out basically as a hard round sphere that the Greeks said was indestructible, right? We now know that if you wanted to draw a picture of it, it would be much better to kind of look like this, right? You've got a tiny little nucleus at the very center. In fact, if you could blow up an entire atom to this size right here, you still would not be able to see the nucleus. It would be that unbelievably tiny. But the electrons are kind of like blinking in and out, almost like in a big cloud as they zoom around at almost the speed of light. We also know that you can split an atom, right? It's not impossible to split an atom. In fact, it happens all the time where we can split atoms and everything. So we know that the Greeks weren't, correct about that. For our final thing, size of atoms, we'll talk about this a couple times and everything. But imagine you blew up the entire atom to the size of an entire football stadium. Right? If that was the size of the atom and right at the very center was the nucleus, well, then it would just be big enough that you could actually see, the nucleus and actually look at it with your own eyes and everything. So the nucleus is just that phenomenally tiny compared to the size of the whole, atom that's going on right there. All right. Hopefully this has helped you out with the fact that the atomic model has changed over time. And make sure that you take the short quiz after, you watch this video.